Okay, so we're going to look at some questions about electromagnetic induction. So the first off, we're going to look at how we can demonstrate electromagnetic induction using a solenoid, a magnet, a sensitive ammeter or a galvanometer, and a connecting wire. So the first thing we need to do is draw a diagram. So let's do that. So we're going to have a coil, and that's going to need to be connected to the galvanometer, which is another word for sensitive ammeter. And then what we're going to do is we're going to have a bar magnet which we can either move into the coil or we can move it out, or we could move the coil. Either way will work. So state two things you could do to induce a current in the solenoid. So the two options are we can move the magnet into the coil, or we could move the coil over the magnet. Both of those things will induce an EMF and therefore a current. So explain why either method induces a current. So, an EMF is induced whenever magnetic field lines cut through a conductor, which whether we move the magnet or we move the coil is being forced to occur. So that's why we get an EMF. Well, we're asked to explain how we get a current. So because a current is induced because the coil is connected in a complete circuit. So cutting magnetic field lines gives you an EMF, and then a complete circuit is what gives you the current. Okay, so those are the 2 points we need to make there. So describe the changes you can make to your answer in B in order to give a current in the opposite direction. So what we need to do is I said move the magnet into the coil in my answer, so we're going to need to move the magnet out of the coil instead of into it. So we essentially need to change the movement to the opposite direction. So whatever we said in B, we need to say the opposite direction here. And describe the change you can make in order to induce a larger current. Well, we'd make to move the magnet, or the coil for that matter, faster. So we get more flux lines cutting per second. Okay, so the diagram shows a dynamo used to power lights on a bike. So essentially what happens is this wheel is rotating that way. That causes this part here to spin. So that makes this magnet spin. So we've got magnetic field lines which cut through this coil here. And you can see the coil is wrapped around a core of soft iron, and we've got that connected. So usually what you do is you connect this to a light bulb, so that a lot of bike lights are powered using these dynamo devices. So why do the coils on the wire have to be insulated? So insulated just means wrapped in some sort of plastic usually. And the reason we do that is to prevent the short circuit. So you notice the coils are wrapped really tightly together. So we need to make sure they're only connected by the fact that it's one wire that's wrapped around. We need to make sure the coils aren't actually touching each other, because that would create the short circuit we refer to. So what's the purpose of the iron core? It's there to increase the strength of the magnetic field, so we get a larger EMF. So whenever you're seeing iron cores used in this electromagnetism topic, it's always there to amplify or increase the strength of a magnetic field, because the iron core becomes magnetized in the presence of magnetic fields. So describe the useful energy transfer occurring in the dynamo. So we've got the bike wheel moving, so we're starting with kinetic energy, and we use it to produce electrical energy, which we might then turn into light or whatever it is. So describe how the brightness of the bulb could be increased. So what we would need to do is increase the wheel speed, because that makes the speed of the rotating magnet increase, and that means the number of flux lines cut per second increases. So that's what we'd need to do, essentially pedal faster. Okay, the other thing we could do is we could increase the number of turns on the coil. So again, we've got more flux lines cutting conductors every second. That would work as well. So the diagram shows a loop of wire which is being moved rapidly downwards between the poles of the magnet. So what I'm going to do is I'm actually going to use Flemings' right-hand rule here to figure out the direction of induced current. So the field is going north to south, so my first finger points that way. The wires are moving down, so my thumb points that way. So we can see we're going to get induced currents in these wires in these directions here. Okay, so we would expect to get it in the same direction in both wires. However, what you'll notice is that if we track those around, those are actually going in the opposite directions around the circuit. So actually nothing is going to happen here at all. So the answer in terms of what's going to happen on the milliammeter is nothing. And the explanation is the currents are induced in the same direction, like we can see, which cancel each other out in terms of the circuit, resulting in zero current. So we could be a little bit pedantic here and say, actually, well, when one wire is going through, we're going to get a current. And then once that wire is exited, we then get a current. But most of the time, they'll be both going through or neither going through. So pretty much most of the time, we're going to get zero current. So electricians can locate electrical cables using a device based on induction. So we can see we've got some sort of galvanometer by the looks of it. We've got a rod through the middle to amplify the strength of the magnetic field, and we've got coils. Okay, pretty standard. So the device is held stationary where the electrician thinks a wire could be. What kind of current can the device detect and why? So the key is the fact it said it's based on induction. So if we've got the device stationary, we must be detecting alternating currents, which in fairness, most electrical stuff are in and around homes, businesses, etc. is, so that's fine. And the reason is because we need an alternating magnetic field in order to induce the EMF in the stationary coil. Okay, so how can the sensitivity of the device be increased? We should explain what sensitivity actually is in our answer. I'm pretty sure that's meant to say sensitivity. So first of all, what is sensitivity? Sensitivity is the change in output divided by the change in input for a device. So let's talk about specifically what that means. Well, if you increase the number of coils, we'd get a larger EMF induced. And in this case, the output is the EMF, because that's what our galvanometer or a voltmeter or whatever it is detecting. So that means the output is increased for the same input. So the input here is going to be essentially the current or the magnetic field around the wire we're trying to detect. If we keep that the same but have more coils, we're going to get a larger EMF. So we've got a bigger output for the same input. So we've got increased sensitivity.